Hi everyone, welcome back to my Engineering Chemistry YouTube channel. In this video, we will discuss about isomerism. Isomerism arises when compounds with same molecular formula, but they have different properties. Okay, and these are called as isomers, and the phenomenon is called isomerism. Okay, we have two different types of isomerism. One is structural isomerism, structural isomerism, and second one is stereoisomerism. Stereoisomerism. Okay, first we will study about structural isomerism and then we will move on to stereoisomerism. Coming to structural isomerism, here structural isomerism is due to the difference in the arrangement of atoms or groups in the molecule. Here, structural isomerism arises due to the difference in the arrangement of atoms or groups, okay, in the molecule. In this structural isomerism, we have four different types. First one is ionization isomerism. Second one is linkage isomerism. And third one is hydrate isomerism. Or which is also called as solvate isomerism. And fourth one is coordination isomerism. Okay, so these are four different types of structural isomerism. First one is ionization isomerism, linkage isomerism, hydrate or solvate isomerism, and fourth one is coordination isomerism. First we will see what is ionization isomerism. Okay, coming to ionization isomerism, here the complex compounds have same molecular formula but produce different ions in the solutions. Okay, these will be having same molecular formula, okay, produce different ions in the solution. Okay, produce different ions in the solution. Okay, this ionization isomerism arises when different counter ions are present. Okay, arises when different counter ions are present. Okay, let us take an example, that is CONH3 5 times, okay, Br, and the counter ion is SO4, and we will consider CONH3 5 times SO4, okay, here Br. Here the counter ion is SO4 and here the counter ion is Br. In solution, what happens? In the solution, it produces the ions. Okay, so that will be CONH3 5 times Br 2 plus SO4 2 minus. Okay, these are the ions produced in the solution. In the same way, here also, okay, CONH3 5 times, SO4 plus Br minus. Consider this is A and this is B. So when you add barium chloride solution, okay, when you add barium chloride solution, A gives white precipitate, okay. A gives white precipitate with barium chloride, okay, BaCl2. Here B does not give B does not give white precipitate with barium chloride, okay, with barium chloride. This evidently shows that the presence of different counterions, okay. In A we have SO4 as a counterion, and in B we have Br as counterion. Here the counterion SO4 2 minus reacts with the barium chloride to give white precipitate. Here the counterion is Br minus, which do not give white precipitate with barium chloride. Okay, we will take one more example, that is CONH3 4 times, Br2, and the counterion is, and next one is CONH3 4 times, BrCl, and the counterion is Br. Okay, so this produces ions in the solution, that is CONH3 4 times, Br2, 1 plus on the coordination sphere plus Cl minus. These are the ions produced in the solution. Here also ions are produced in the solution, that is CONH3 4 times, BrCl plus, okay, 1 plus Br minus. Okay, these are the ions produced in the solutions. When this is treated with AgNO3, what happens here? We have Ag plus and NO3 minus. This Ag plus reacts with Cl minus to give AgCl, which is white precipitate, which is white precipitate. Again, if you treat this with AgNO3, what happens is AgNO3. Here we have Ag plus and NO3 minus. Here Ag plus reacts with Br minus to give AgBr, which is pale yellow precipitate. Okay, here we are getting white precipitate because here the counterion is Cl, and here we are getting pale yellow precipitate, that is because of the counterion is Br. Therefore, these two are examples of ionization isomerism. Okay. Next we will see what is linkage isomerism. In linkage isomerism, complex compounds have same molecular formula, okay, but ligands bonded to the central metal atom, through different donor atoms, okay, through different donor atoms. Okay, linkage isomerism arises when ambidentate ligands are present. Okay, we will take some examples. That is cobalt, we have NH3 5 times, and here we have NO2. Okay, and the one more complex compound is cobalt, NH3 5 times, ONO. Okay. Here we have two different ligands. One is NH3 and another one is NO2. Here also we have two different ligands. One is NH3 and another one is ONO ligand. Okay. So in NO2 ligand, okay, the donor atom is nitrogen. In NO2, nitrogen is the donor atom. Nitrogen is the donor atom. And coming to ONO, oxygen is the donor atom. Donor atom. Okay, here this NO2 is named as nitrito-N. Nitrito-N. Here this ONO ligand is named as nitrito-O. Nitrito-O. In linkage isomerism, the ligand bonded to central metal atom through different donor atoms. Okay, we will see few other ligands which gives rise to linkage isomerism are, okay, first one is Cn minus, which is named as cyanido, and we have Nc minus, which is named as isocyanido, and we have one more, that is SCN minus. Okay, this ligand is named as thiocyanito-S. Thiocyanito-S. If you write NCS minus, this is named as thiocyanito-N. Okay, here sulfur is the donor atom and here nitrogen is the donor atom. These ligands gives rise to linkage isomerism. Next we will move on to hydrate isomerism. Hydrate isomerism, which is also called as solvate isomerism. Solvate isomerism. In this isomerism, what happens is complex compound have same molecular formula, but water molecules are exchanged inside and outside the coordination sphere. Okay, hydrate isomerism arises when H2O is act as ligand as well as present as free solvent molecules in the crystal lattice. Okay, so hydrate isomerism or solvate isomerism arises when H2O is act as ligand as well as present as the free solvent molecules in the crystal lattice. We will take example, that is first one is, okay, Cr H2O 6 times Cl3. Okay, and the next one is, again we are taking Cr H2O 5 times Cl. Okay, in the first case 6 H2O ligands are present, in the second case 5 H2O ligands are present, and the counter ions will be here Cl2 and H2O. We will consider one more case, that is Cr H2O 4 times Cl2, and the counter ions will be Cl2H2O. So here how many H2O ligands are there? Here 6 H2O ligands are there. Here 5 H2O ligands are there. And in the third case we have 4 H2O ligands. If you compare all three cases, so the molecular formula is same, but the water molecules are exchanged inside and outside the coordination sphere. Okay. Therefore, these are examples for hydrate isomerism, which is also called as solvate isomerism. Next, we will move on to coordination isomerism. coordination isomerism. So what happens in this coordination isomerism means, this coordination isomerism arises when ligand or central metal atom is exchanged. Okay, is exchanged. We will take example. If you consider CONH3 6 times, CONH3 6 times, and along with that we have CN 6 times. Okay, so what happens in this case is, here these two ligands are exchanged, so that we are getting CN 6 times. Okay, and another one is, it is NH3 6 times. Okay, so here what happened? Here the ligands are exchanged. Okay, in the first case cobalt is coordinated with 6 NH3 ligands, and in the second case cobalt is coordinated with 6 CN ligands. Okay, again in the first case chromium is coordinated with 6 CN ligands. In the second case chromium is coordinated with 6 NH3 ligands. Therefore these two are the example for coordination isomerism. Next type of isomerism, that is stereoisomerism. Stereoisomerism. This will be having same chemical formula, same chemical bond, same chemical bond. Okay, but different spatial arrangement. Okay, stereoisomers will be having same chemical formula, same chemical bond, but the spatial arrangement is different. Okay, again this stereoisomerism is classified into two different types. One is geometrical isomerism, and second one is optical isomerism. Geometrical isomerism, which is also called as cis-trans isomerism. Okay, so here you have to remember three important points. One is square planar and octahedral complexes. Square planar and octahedral complexes contains at least two similar ligands. Contains at least two similar ligands. Next point is, if similar ligands present on same side gives cis isomer. Next point is, if similar ligands present on opposite side gives trans isomer. Okay, in geometrical isomerism you have to remember that square planar and octahedral complexes contains at least two similar ligands. And next one is, if similar ligands are present on the same side gives cis isomer. If similar ligands present on the opposite side gives trans isomers. And tetrahedral geometry does not exhibit geometrical isomerism. We will see why it is. Okay. If the coordination number is equal to 4 in tetrahedral geometry, first we will write the structure. Here metal atom, here A, here it is B, here C, and here D. The angle between these ligands 109.5 degree. The relative angles between all these atoms are 109.5 degree. Okay. And the position of all four atoms are identical. Therefore, it does not exhibit geometrical isomerism. Okay, that is because of the position of all four atoms are identical. Okay, positions of all four atoms are identical. Therefore, tetrahedral geometry does not exhibit geometrical isomerism. In square planar geometry, we will see what happens. Okay. So the square planar geometry means this is the structure, right? Here there is a metal atom. Here A, and here we have A, here B, and here B. Okay. This is square planar geometry. So here the angle between these two atoms is 90 degree. And here also angle between these two are 90 degree. In this case, if you pass the plane like this, here similar ligands are present on the same side, right? If similar ligands are present on same side, okay, similar ligands on same side gives cis isomer. Similar ligands on opposite side gives trans isomer, right? Gives trans isomer. So if you pass the plane like this, okay, here similar ligands are present on the same side. Therefore, this is cis isomer. Now, if you exchange these two atoms, what happens? Here metal, okay, here we will be having A, here B, here A, and here B. Okay. So again, if you pass the plane, okay, what happens here? Here similar ligands are present on opposite side. Here the similar ligands are present on opposite side. Therefore, it is trans isomer. If you take the complex, okay, and here number of geometrical isomers, okay. If the complex is of Ma2B2 type, how many geometrical isomers are possible? So this is 2. Okay, if you take an example, that is PT NH3 NH3, here Cl and here Cl. Okay. So here if you pass the plane, two same ligands are present on the same side, therefore it is a cis isomer. Again, if we exchange these two ligands, what happens? Here Pt, here platinum, here NH3 Cl, and here NH3, here Cl. So what happens when you pass the plane? So same type of ligands are present on opposite direction, therefore it is trans isomers. How many isomers are possible for the complex of Ma2B2? It is 2. Therefore, the number of geometrical isomers are 2. If you take Ma2BC, A2BC type of complex, the number of geometrical isomers possible are 2. For example, here metal, here we have A, B, A and C. Okay, this is Ma2BC complex. Okay, here we have 2A and 1B and 1C. So here if you pass the plane, two same ligands are present on opposite side, therefore it is trans. Okay, if you exchange these two ligands, what happens? Again you write M, here we have A, here A, B and C. Okay, again if you pass the plane, here two same ligands are present on the same side, therefore it is cis. Therefore two geometrical isomerism are possible for Ma2B2 type of complex. Okay, if you take MABCD type of complex, three geometrical isomers are possible. Okay, and if you take MAB2, MAB whole twice type of complex, the number of geometrical isomers possible are 2. Okay, here ABCD or monodentate ligands or monodentate ligands. Okay, and coming to A and B, it is unsymmetrical didentate ligand. Okay, unsymmetrical didentate ligand. Didentate ligand. Unsymmetrical means which consists of two different donor atoms. Okay, this is about the geometrical isomerism in square planar geometry. Next we will go for octahedral geometry. Here you have to remember this table because it is very important on point of examination. So now we will see the geometrical isomerism in octahedral geometry. So for that the coordination number should be equal to 6. Okay, so it gives octahedral geometry. In octahedral geometry we will see geometrical isomerism. Okay, here we will write the complexes and here we will write number of geometrical isomers possible. Number of geometrical isomers possible. First we will consider the complex of Ma6 type. Ma6 type of complex. If you write the structure of Ma6, here consider we have a central metal atom M to which 6 identical ligands are attached. Okay, 6 identical ligands are attached. Okay, these 4 are in the same plane, these 2 are in the opposite planes. Okay, so here since all 6 ligands are identical, so if you exchange any one of these ligands with any other position, that is not going to make any changes. Therefore in the complex of type Ma6, the geometrical isomers cannot be seen. Next we will consider Ma5B type of complex. Okay, again we will write the structure of Ma5B type of complex. That will be like this. Okay, it is an octahedral complex in which 5 same ligands are attached. Okay, one different ligand. So these are in the plane. Here also only one different ligand is attached. So in this case, if you exchange the position of B with any position of A, so it is not going to make any changes. Therefore, in the complex of type Ma5B, we are not going to see any geometrical isomers. Okay, next is Ma4B2 type of complex. Ma4B2 type of complex. If we write the structure of Ma4B2, okay, here 4 identical ligands are present, that is A, and we have 2 ligands of type B. So here these 4 ligands are in the plane, okay, and 2 ligands are in the opposite plane. Since these 2 ligands are in the opposite side, this gives trans isomer. This gives trans isomer. If you write one more structure, okay, here we have A and A. Here we have B and B. So in this case, these 4 ligands are in the plane. This is above the plane and this is below the plane. So in this case, here the angle between these two ligands is 90 degree. Therefore, it is cis isomer. Therefore, it is cis isomer. For the complex of type MA4B2, the number of geometrical isomers possible are 2. Okay, one is trans and another one is cis. Next, we will move to another complex, that is MA4BC. Okay. In this type of complex, number of geometrical isomers are 2. Next, we will consider the complex of MA3B3. So in this type of complex, the number of geometrical isomers are 2. Next one is MA3. Now we will split B3 into B2C. Okay, B2C. So in this type of complex, the number of geometrical isomers possible are 3. Okay, next we will write one more complex, that is MA3. Now we will split B2, that is B, C and D. So here the number of geometrical isomers are 4. Again we will take another complex where we are going to have MA2, B2 and C2. MA2, B2, C2. So here we are going to have the geometrical isomers 5. So next complex MA2, B2. Now we will split C into CD. So here the number of geometrical isomers are 6. Another complex that will be of type MA2, BC, DE. Okay, in this type of complex we are going to have the geometrical isomers 9. Now we will split A2. So therefore all 6 ligands will be different. Therefore M, A, B, C, D, E, F. Okay. So in this case, the number of geometrical isomers possible are 15. Now we will consider M, AA all twice, B2. Okay. So in this type of ligand, number of geometrical isomers are 2. So now we will split B2. Therefore M, AA twice, BC. Okay. In this type of ligand, geometrical isomers are again 2. If you consider M, AB all thrice type of complex, number of geometrical isomers possible are 2. Here you have to note down that here A, B, C, D, E, F are monodentate ligands. Monodentate ligands. Okay. Again, AA is symmetrical didentate ligand. Didentate ligand. Again, AB is unsymmetrical didentate ligand. Unsymmetrical didentate ligand. Okay, so you have to remember this table. Okay, so it's very easy to remember this table. Here MA6 type of complex and MA5B type of complex will be not having any geometrical isomers. Therefore, you have to start remembering from MA4B2. So the trick is, here it starts with 222, okay, 222, 3, 4, 5, 6, 9, 15, 222. It starts with 222, 3, 4, 5, 6, 9, 15, 222. This is how you have to remember, okay. So among this, okay, MA3B3 is very important type of complex. Based on that, we will be having questions. Now we will see what type of questions you can expect from MA3B3 type of complex. If you write MA3B3 type of complex, first we will write the structure of MA3B3. So what happens is, here M, to which 6 ligands are attached. Out of that, 3 will be same ligands and another 3 will be same. Okay. So these 4 are in the plane. Okay, this is in the opposite plane and this is also in the opposite plane. Here out of these 3 ligands, the triangle is made. Okay, the triangle is made. So here this A and this A will be in the same plane. will be in the same plane, and here this will be in the opposite plane. Opposite plane, and this type of complex gives facial isomerism. Okay, in short, it can be written as FAC. Okay, in this type of isomer, out of three similar ligands, two ligands are in the same plane and one ligand will be in the opposite plane. Okay, so this type of complex gives rise to facial isomerism or facial isomer. Now we will write another structure. So that will be like this. Here M, again 6 ligands are attached. Consider A, B, A, here we have A, B and B. So here these 4 ligands are in the plane. This is above the plane and this is below the plane. So in this case what happens is 3 ligands of same type will be in the same plane. 3 ligands of same type will be in the same plane. Okay, same plane. So therefore this type of isomer is named as meridional. Okay, it is meridional isomer. In short, it can be written as MER. Again, coming to facial isomer, out of 3 similar ligands, 2 ligands are in the same plane and one will be in the opposite plane. So which gives rise to facial isomer. And coming to meridional isomer, 3 similar ligands are in the same plane, which gives rise to meridional isomer. Next, we will consider the complex of type MAA all thrice. AA is symmetrical didentate ligand. Didentate ligand. If you write the structure, so here we will be having central metal atom M, to which 6 donor atoms are attached, okay, which are identical. Identical. So it will be like this. Okay, since it is symmetrical didentate ligand, this will be the structure. In this complex, all 6 donor atoms are identical, therefore it does not exhibit geometrical isomerism. Okay, this is all about geometrical isomerism. Now we will start optical isomerism. Optical isomerism. In this optical isomerism, coordination compounds will be having same molecular formula, but different in the direction of rotation of plane polarized light. Different in the direction of rotation of plane polarized light. Okay, so optical isomers will be having same molecular formula but different in the direction of rotation of plane polarized light. Okay, so these are called as optical isomers. Here optical isomers are non-superimposable mirror images. Non-superimposable mirror images. Okay, mirror images. These are optically active. Okay, these are optically active. Let us take an example that if you consider A, if you write the mirror image of A, it will be like this. Okay, if you place both A on top of each other, it is resulting to give A. Okay, that means it is superimposable. Okay, so this is superimposable mirror image, which is called as non-enantiomer, which are optically inactive. Okay, which are optically inactive. Here non-superimposable mirror images are called as enantiomers. Okay, enantiomers. Again, we will consider one more case. Okay, that is, if you consider P, okay, if you write the mirror image of P, how it looks, it will looks like this. Okay, no matter how the structure is rotated, it cannot be put on the top of another with all points matching. Okay, if you place these two on top of each other, what happens? It will be like this. Okay, so it gives the image like this. So this is nothing but non-superimposable mirror image. Non-superimposable mirror image. That means non-superimposable mirror images are called as enantiomers, right? Enantiomer. This is an enantiomer, which are optically active. Okay, which are optically active. Based on this information, we will see the optical isomerism in tetrahedral geometry, square planar geometry, and octahedral geometry. In coordination number 4, okay, first we will consider tetrahedral geometry. Okay, tetrahedral geometry. So if you write the structure of tetrahedral molecule, so here the central metal atom, here ligands are attached, it is B, A, it is D, and it is C. So in this case, the angle between the ligands will be 109.5 degree. Here the relative angle is same, that is 109.5 degree. The position of all the atoms is same. So here the position of all the atoms, positions of all the atoms are same or same. Therefore, optical isomerism cannot be seen in isomerism cannot be seen in tetrahedral geometry. So optical isomerism cannot be seen in tetrahedral geometry. And now we will consider again in coordination number 4, square planar geometry. Okay, so now we will see what happens in square planar geometry. First we will write the structure of the compound. So it will be like this, right? Yes, this is the structure of square planar geometry, A, B, C, D. So here all these ligands will be in the same plane. So in this case, what happens is, here all the atoms will be in the same plane. Okay, here all the atoms will be in the same plane. All the atoms will be in the same plane. Therefore, the plane of symmetry is existent. Okay, due to the plane of symmetry, due to the plane of symmetry, in square planar geometry, optical isomerism cannot be seen. Therefore, in this case also, optical isomerism cannot be seen. Optical isomerism cannot be seen. Okay, cannot be seen in square planar geometry. In tetrahedral geometry, the position of all the atoms are same. Therefore, the optical isomerism cannot be seen in tetrahedral geometry. Coming to square planar geometry, all the atoms will be in the same plane. Therefore, the plane of symmetry is possible. Due to the plane of symmetry, optical isomerism cannot be seen in square planar geometry. Now we will see optical isomerism in coordination number 6. Okay, in coordination number 6, we're going to get octahedral geometry. Here first we will write down the complexes. Next we will write down enantiomer pair. Okay, for Ma4B2 type of complex, symmetry is possible. Okay, symmetry is possible. Therefore, the enantiomer pair is 0. Okay. Next, coming to MA4BC, here also symmetry is possible. Again, enantiomer pair is 0. Again, in MA3B3 type of complex, here also symmetry is possible. Therefore, enantiomer pair is 0. And coming to MA3B2C, here also symmetry is possible. Therefore, enantiomer pair is 0. Next, coming to MA3BCD type of complex. So, what happens is here the enantiomer pair will be 1. Okay, enantiomer pair will be 1. And next one is Ma2B2C2. Here also enantiomer pair will be 1. And coming to Ma2B2CD, here the enantiomer pair will be 2. Next, coming to Ma2BCDE type of complex, here enantiomer pair will be 6. Okay. Next one is MABCDEF. Okay, here all the ligands will be of different types. So in this case, the enantiomer pair will be 15. Next, coming to MAA all twice B2. Here you are going to get one enantiomeric pair. Next one is MAA2BC. So here again you are going to get one enantiomer pair. So in the type of MAB thrice. Okay, MAB thrice. So here you are going to get enantiomer pair 2. Now we will see how many of them are optically active. Okay, optical activity. In the first case, due to the symmetry, there is no enantiomer pair, therefore it is optically inactive. Optically inactive. So second one, again it is optically inactive. Here also due to the symmetry, it is optically inactive. Here also it is optically inactive. Next, coming to MA3BCD type of complex, it is optically active. Okay, optically active. Here it is optically active. Again here it is optically active. Remaining all are optically active. Okay, optically active. Next, we will write down the geometrical isomers for the complexes that we have mentioned here. Okay, so the geometrical isomers possible for Ma4B2 type of complex is what? It is 2. Okay, so I gave you the trick that it should be triple 2. Okay, 3, 4, 5, 6, 9, 15, 9, 15, again triple 2. Okay, this is how you can remember. So this is how you can easily remember. Okay, it is triple 2, 3, 4, 5, 6, 9, 15, triple 2. Okay, now we will write the possible stereoisomers for the complex that we have taken here. Okay, so here we will write stereoisomers. Okay, now we will write the possible stereoisomers for the complex that we have taken here. Okay, here you can calculate the number of stereoisomers. Okay, by adding number of geometrical isomers plus enantiomer pair plus enantiomer pair. Okay, enantiomer pair. So here 0 plus 2 is 2. Again 0 plus 2 is 2. Next 2. 0 plus 3 is what? 3. Next 1 plus 4, it is 5. Next 1 plus 5, 6. 2 plus 6, it is 8. Next 6 plus 9, it is 15. Next is 15 plus 15, it is 30. Okay, next 2 plus 1 is 3. Again 3 and again 3. Okay, these are number of stereoisomers obtained, okay, for the complexes that we have mentioned here. Okay, for the complexes that we have mentioned here. Next we will take few other complexes of octahedral geometry. Okay, we will see that. Now we will consider the complex of type MAA all twice B2. Now we will write the structure of this complex. Okay, it will be like this. Okay, M, to which two didentate ligands are attached. Here A, it is a didentate ligand. Here we have A and A, it is a didentate ligand. Here we will be having B and B. Here these ligands are in the plane. Okay, this is above the plane and this is below the plane. Here two similar ligands are in opposite direction. Therefore, it is a trans isomer. Okay, it is trans isomer. It is optically inactive. Optically inactive. Okay, because of plane of symmetry. Plane of symmetry. Next, we will write the cis isomer of this complex. It will be like this. Okay, M, here B, B, Okay, here A and A. Okay, these are bidentate ligands. So if we write the mirror image now, if you write the mirror image, okay, so here we have B, here we have A, okay, again here B, A and A. Okay, these are didentate ligands. Okay, these two are mirror images which are non-superimposable mirror images. Okay, so this is cis form of isomer. So in this case, we are finding out non-superimposable mirror images. Therefore, it is optically active. Okay, these two are non-superimposable mirror images. Non-superimposable non-superimposable mirror images. Okay, mirror images, therefore it is optically active. It is optically active in the complex of type MAA all twice B2. Okay, trans isomer is optically inactive. Trans isomer is optically inactive and cis isomer is optically active. Okay, next we will consider another type of complex. Okay, that will be of type MAB all twice C2. Okay, MAB all twice C2. Now we will write the structure of this complex. Okay, so it will be like this M. Okay, here we have A, B, A, B, and here C, C. So here A and B are unsymmetrical didentate ligand. Now we will interchange this A and B. Okay, then we will see what happens. Again, if you write the structure here M, here A, B, here it will be B, A, C and C. Okay, this is the structure we got. Okay, after interchanging this A and B, we will interchange this A and B. Okay, M, here we have B, here A, here B, A, C and C. Okay, now we will send these two ligands to the opposite direction. What happens? Okay, so this comes here and this comes here. So here we will be having metal. Okay, here C, and here it is A, B, and here we have A and B. Okay, now we will interchange these two. So we are getting M, here we have C, here it is B, here A, and here it is A, and here it is B. Okay, this is structure 1, 2, 3, 4, and 5. These are 5 structures. So we have 5 possible structures for the complex of type MAB all twice C2 type of complex. Okay, so now if you write the mirror image for the structure 1, you will get non-superimposable mirror image, therefore it is optically active. Okay, it is optically active. Coming to second case, if you write mirror image, you will get non-superimposable mirror image, therefore it is also optically active. Again, coming to third case, if you write the mirror image, okay, you are getting non-superimposable mirror image, therefore it is optically active. Next, coming to fourth one, if you write the mirror image, you are going to get superimposable mirror images, therefore it is optically inactive. Okay, next fifth one, here if you write the mirror image, what happens? Here you will be having central metal atom, here C and here C. Okay, it is B, here A, and here it is A, and here it is B. So these two are non-superimposable mirror images, therefore this is optically active. Okay, out of 5 structures we have only 4 enantiomeric pairs. 4 enantiomeric pairs. Next, coming to another type of complex, okay, which is MAA all thrice. Okay, if you write the structure of this complex, so here it will be M, okay, to which 3 didentate ligands are attached. A, 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 A and A. Okay, since it is a didentate ligand, this will be the structure. Okay, if you write the mirror image, okay, so the mirror image is, here we have A, here A and A. Okay, so this is the mirror image. Consider this is A and this is B. Now if you place both on top of each other, you're going to get non-superimposable mirror image. Non-superimposable mirror image. Non-superimposable mirror image. Therefore, it is optically active. Okay, it is optically active. So this type of complex exhibits optical isomerism. Exhibits optical isomerism. Optical isomerism. Example, okay, Cr En all thrice. Okay, the charge on the complex will be 3 plus. Okay, this is an example for the type of complex MAA all thrice. This is all about isomerism in coordination compounds. In the next video, we will discuss about Werner's theory. If you found this video useful, do like, share and subscribe. Thank you for watching.